In this video, we're going to talk about beam analysis. Beam, structural member that carries a load that is applied transverse to its length, used in floors and roofs, may be called a floor joist, a stringer, floor beams, or girders. We already talked about chasing the load a little bit. Let's review. The loads are initially applied to a building, surface, floor, or roof. Loads are transferred to beams, which transfer the load to another building component. Again, these are beams, where my mouse is. These are girders, which connect to columns and then transfer the load down to the ground. Static equilibrium, the state of an object in which the forces applied counteract each other so that the object remains stationary. A beam must be in static equilibrium to successfully carry loads, and that's what we want our buildings to do. We want them to be in static equilibrium. The loads or forces applied to the beam from the roof or floor must be resisted by forces from the beam supports. The resisting forces are called reaction forces. Note that forces are often referred to as vectors because they have a magnitude and a direction. Reaction force. Reaction forces can be linear or rotational. A linear reaction is often called a shear reaction. A rotational reaction is often called a moment or a moment reaction. The reaction forces must balance the applied forces. Beam supports. The method of support dictates the type of reaction forces from the supporting members. So here's a roller, meaning it has a reaction in the y direction only because it is free to move left and right. A pin support, again, is resting down in the y direction. That's why it has a reaction force going up. And we're assuming that the beam is pushing on the support. That's why it has a reaction pushing back. Fixed support, like a cantilever, it has both the X and Y reaction forces, and it has a rotational moment force because the end of the beam wants to push down, so the fixed end wants to rotate up. Some simple beam types. Simple, continuous, meaning it'll have continuous support, or a cantilever, like we just talked about. Fixed, we can have moments at both ends. A propped, fixed at one end, supported at the other, or some type of overhang. Okay, simple beams, applied load. Here's our free body diagram. When there is no applied horizontal load, you may ignore the horizontal reaction at the pinned connection. That's a good point. We always draw it on there, and the X and Y reaction loads on the pin side and the Y reaction load on the roller side are what I usually call our templates. They could change direction, or like this says, they could be non-existent, depending on our problem. Okay, this should be a review. Fundamental principles of equilibrium. Summation of all the forces, X, Y, and moment, all need to equal 0. That's the basis for all these calculations. Moment, created when force tends to rotate an object. The magnitude of the moment is equal to the force times the perpendicular distance to the force, or the moment arm. There's our force, there's our perpendicular distance. Moment is force times distance. Okay, here's a sketch of a beam diagram. Let's make ourselves familiar with this. We have some dimensions, 6 feet to our point load. P stands for point load of 4,000 pounds. Total distance of 20. From the point load to point B is 14 feet. Here's a pin, here's a roller, point A and B. This is a 650 pounds per foot. This is a uniform load across the entire beam. Okay, our free body diagram. We just replaced our pin and our roller and drew and wrote our reactions. Okay, I'm actually going to do this a little bit out of order. I like to calculate the moment first. This is the toughest one. So the sum of the moments needs to equal 0. We're going to assume that a counterclockwise rotation is positive. So counterclockwise is positive, clockwise would be negative. What they're doing in this equation right here is they are summing, sigma, they're summing all of the moments. So they happen to start on the right, that's fine. I usually like to start on the left-hand side at the pin connection. FYB, we don't know it, but we still need to take it into account. FYB, and that's the force, and its perpendicular distance to the pin is 20 feet. That's how they get FYB 20. Why is it positive? Because if you think about it, it's rotating counterclockwise. We just said counterclockwise is a positive moment. Next one, 4,000 times 6 feet. Perpendicular distance. It is a negative moment. That's why there's a minus sign here. Another way you could write this is you could say plus negative 4,000 times 6. However you want to keep track of it, but keeping track of those signs is absolutely extremely important. Next one they did is 13,000. Now let's talk about where they get this 13,000 from. Let's back up here. They took the 650 pounds per foot times 20 feet, and that became an equivalent concentrated load of 13,000 pounds. That's where they get this number from, times 10 feet, because it's 10 feet to the pin, and it's a negative moment. Plus FYA times 0. You don't have to do this. Why is it 0? Because our reference point is at point A. Here's our force. What's its distance? 0. You don't even need to include it. But the sum of all of these has to equal 0. So they do all the math, and that's how we get FYB. Remember, that's what we were solving for. FYB equals 7,700 pounds. If you want to prove it to yourself, plug this back into here. All of this will equal 0. So now let's backtrack. I like to do moments first. That's just a personal preference. X forces. Normally we are not going to have any X forces. Some of the forces in the X direction are 0. There are no X forces. 0. Then we do our Y forces. The sum of the Y forces must equal 0. They went about this a little bit differently, but it's the same principle. They said that FYA plus FYB must equal 17,000. Well, that makes sense because 13,000 pound load and our 4,000 pound load equals 17,000. Newton's third law, whatever's pushing down has to be pushing back up. Again, there's our concentrated load turned into a point load. We already found FYB, that was 7,700 pounds. And if we do that, here we go, FYA plus 7,700 pounds equals 17,000 pounds. FYA must be 9,300 pounds. Y forces, notice that this is positive because it's going up in the positive direction, and same with the 7,700. This isn't saying anything new. Okay. Now let's talk about a shear diagram. Here's our beam that we just solved for. We solved for forces at point A and point B in dark blue right here. Nothing's changed. Now let's talk about our shear diagram. Our shear diagram is kind of like good bookkeeping. You can think of it as a diagram of the forces, the shear forces pushing on our beam. So let's talk about these units. Each square going up is about 3,000 pounds, and say 3, 6, 9, 9,300 pounds. And each square going to the right, across rather, is about 2 feet. That's not extremely important. So we draw our shear diagram and we start out at 9,300. Why? Because The reaction force is pushing up 9,300 pounds. My beam is pushing down 9,300 pounds. That's why we started up here at 9,300 pounds. So I start walking across my bridge or my beam. What forces am I encountering? Well, right off the bat, I'm encountering this uniform load at 650 pounds per foot for 6 feet equals 3,900 pounds. So that's how I get this slope. Then what happens? Well, notice right here I have a point load. A point load of 4,000 pounds. Yes, it's really important that we write all of these. Then notice my uniform load then continues all the way down until 7,700 pounds. Notice we get this 1,400. The reason we get this 1,400, we need to make sure that from where my mouse is, or where my pointer is from here to here, has to equal 9,300 pounds. So 3,900 plus 4,000 plus 1,400 equals 9,300. Another way to do that is take 9,300 minus 3,900 minus 4,000. That will equal this 1,400 pounds. And that's going to become important in just a second. Shear at a point along the beam is equal to the reactions upward minus the applied loads downward to the left of that point. This point right here, the shear is 0. Everything to the left of this point is about to become very important. Okay, so now we need to find our maximum moment. Think about a diving board. When I barely step out on the diving board, there's not much moment. And I keep going further and further and further and further to the edge of the diving board. Right here becomes the maximum moment. Notice that there's no rotational or maximum, there's no rotation or moment at each end of the beam, but there's a lot right in the middle, and that's what we care about. Also notice they say that there's a kink in the moment curve. Well, why? Well, look up. What happens right here? There's a point load. So there'd be a tiny little dip. A tiny little dip is what they're trying to say. A dip in this curve. On a uniform load, though, you're going to have it's parabolic. You're going to have a perfect curve. But ours has a little kink because we have this 4,000 pound point load. All right, I said we need everything from the left of this point where the load crosses this shear point is going to be important, as well as the distance. So we know that from here to here is 6 feet, but we don't know this x, and we need to solve for that. Well, just think about rise over run. We need to solve for our run. We know that this is our rise, 14,000 pounds. 650 is our slope. So that's how we get 2.15 feet. That's important. Okay, there's two ways to do this. This is actually the harder way, and I'll explain a little easier way in a second. We want to find the moment at this point, at point P. Okay? So that moment, here it is in blue, the sum of the moments must equal 0, right? So I want to find this moment, and then they just start adding all the moments that we already know about. So 4,000 times 2.15 feet plus 650 times 8.15 feet. 650 is our uniform load. It's spanning a distance of 8.15 feet. And we did 8.15 feet divided by 2, because that's like putting that load right in the middle. That's why it's times 2, or divided by 2, because it puts it right in the middle. Minus 9,300 pounds right here times 8.15 feet. So all of my moments are taken care of. Let's talk about direction. So this rotation with my mouse This clockwise is negative, right? Clockwise is negative. The 650 pounds, positive. The 4,000 pounds is also positive because it's a positive, it's a counter-clockwise rotation. So that's how we get 45,608 foot-pounds. Now I said this was the harder way. Watch. You get the same thing if you simply take the area of everything. If you simply take the area of everything to the left of the shear, all of this area in yellow. So we have two triangles and a rectangle. Area of a triangle, of course, half base times height. Half base times height plus our rectangle plus half base times height. Look at that, you get the same answer. I think that's a little easier. That's how I would do it. Okay, this just talks about a simple example beam with a uniform load, 1,090 pounds per foot, a uniform load. It spans 18 feet. You tell me, what is what's the shear and the moment curve going to look like with just a uniform load? Well, if you guessed a perfect slope or diagonal, you're right. And if you guessed a parabola, you were right. Okay, that is beam analysis, and stay tuned for the next one where we will calculate some more loads.